Okay, great.
My robots keep falling down. Robots are no good at manipulation. Okay, I think the open problem we all need to think about, and it's, oh, that's even harder, but okay. I think the open problem we all need to think about is feedback control through contact. Okay, so, yeah. All right. We have to, that she's doing that for me, but.
That's Mrs. Critter. Do you not want it?
Maybe not yet, just because of this.
Can you just close my laptop?
It doesn't work yet.
Okay, so we actually saw a bunch of initial examples of this earlier today about planning through contact. We saw, so Ashwin talked about the citability, and Will talked about some asymptotically optimal versions, and this is all good for planning. I think that's awesome, but I think we need more. If we want my robots to stop falling down, I need feedback control, okay? And I actually think there's a very geometric combinatorial problem sitting here that you guys are probably they're exactly the right crew to help us solve, that I want to make sure is on your radar, okay? So I really think this problem is sort of shockingly in the middle of everything we're trying to do with robotics. Anytime you're touching the world, whatever, and it's embarrassing that we have almost no solutions through this. And I'll even make it easier. I don't need general feedback control through contact. I'd be happy if it's sort of local. So I'll allow linearization. Okay, linearization's okay. But I want it to be reliable. Okay, so I want to be able to know that I'm going to be able to, if I give you a contact problem, then I'll be able to just turn a crank and get a solution out. And maybe the analogy I want you to think about is linear quadratic regulators for smooth systems. So if I take a quadrotor as dynamics, right? It's a smooth dynamical system. If I linearize it around a fixed point, I can just solve a Riccati equation and find a stabilizing controller. And LQR is actually great for a lot of reasons. So not only does it give me stabilizing controllers, but sort of for any choice of Q and R, if you follow me, for any positive semi-definite Q and any positive definite R, I will get a stabilizing controller out. And it's sort of got enough richness that I can change Q and R around and change my controller, but still guarantee that it's always going to work, and it's a very reliable process. So if I take that same thing, and I'm a robot with contact with the world, and this is a fixed point, and I say, give me a locally stable controller for this that can possibly make and break contact, right? I've got nothing. I've got nothing to give you. It's really sad. Okay, now, but there's hope, and it's just a geometry and a combinatorial problem, I think. So how many people know what explicit model predictive control is? Awesome. Okay, so just could you solve that for me? That's sort of what I wanted to get towards is I'd like you to, this is one approach to the problem, is solving the explicit MPC problem. But for contact, I need a little bit more than the traditional solution. I need this to be for mixed integer. Sorry, that makes it harder. Model predictive control. But I'll make it easier because I think approximate is fine. And I think that's where the real gems are waiting, is to come up with approximation algorithms of the ilk that you guys have done incredibly well in planning and other things. So let me just make sure that people realize the basic form of that problem. But the goal of the whiteboard and the non-slides is to make this interactive. So maybe, you know.
I have a comment here.
Yeah.
The work of Yuval Tassa in the group of Todorov, he did something where you have, like when you have these contact things, something drastic happens, right? It's not smooth, but he could smooth that out by basically anything that was non-continuous, just to have a smooth approximation, and just use iterative LQR on the entire system. And he was able to do LQR on walking humanoids in simulation. Is that what you're looking for, or is it something different?
So that is that's an approach that I like, that is close to what I'm looking for. I actually think It doesn't work that well on real robots if you push me on it. Okay, and because you have to get rid of that smoothness assumption. We've done similar work where we keep that as a strict assumption, and it's surprisingly difficult to map that, just the plans, directly to execute on the robot. The key problem is, if you have a plan and you want to stabilize it, that's hard. If you can plan on the fly fast enough, that's good, but your plans have to match the real dynamics, and that's tough with the approximate contact models.
Maybe you should be a bit more explicit of what you mean by approximate.
Good. Okay, so so model predictive control. Let me give you the three-line sort of explanation for this. Okay. All right, so for model predictive control for a linear system, I can just take my linear dynamics and some sort of quadratic objective, right? So minimize the sum over n, xn transpose qxn plus u transpose run, with those being positive, definite, and semi-definite. Okay, and I can have some constraints like actuation limits or some state constraints. Maybe they can be more general. All right, so I can solve this, of course, for a particular initial condition. The planning problem for this is just solving a quadratic program. Right, that's the key thing. So if I don't have any constraints, then that's LQR, and I can solve it in closed form. If I add these constraints, these linear constraints, I can still solve it as a quadratic program from a single initial condition. Okay, so that's well known, well understood, awesomely good. The cool thing, the explicit MPC says, what happens if I change my initial condition? Normally the initial condition is given to you, you solve, you execute the first U, and then you move on. Okay, that is a policy, right? That is a controller that I can run. I could ask, how does that change over initial conditions? Turns out the initial conditions also enter the QP in a quadratic, or the cost in a quadratic way. So you can ask, you can just look at the KKT conditions for this, and after solving one single trajectory, you can look at locally what happens. If the active set doesn't change on that solution, by solving that one initial condition, you can see that locally the feedback policy is piecewise, is affine, okay? And the cost to go is quadratic locally. And in fact, if you look at where the active set changes in the KKT conditions, you can see that optimality is true on a polytope, okay? So there is a set of half-plane constraints that tell me when that active set of that solution stops being valid. So it turns out the whole explicit solution, if I were to plot this for lots of initial conditions, then the controller that comes out of this is piecewise affine, polytopic. It's a bunch of polytopes in the plane, right? If I plot x1 versus x2, whatever, I get a control policy that lives on a polytope, and in each section it's affine controller. It's piecewise. It's quadratic. The controller is continuous. There's a lot of things we know about this, and you get it all from just solving the QP at one point. You instantly learn about this. That's sort of the explicit MPC problem. Okay, we could do the same thing through contact. Contact changes a little bit. I mean, basically, you get a contact force here. I can go into the details if you like, but if you get you get some forces that come in like this, and then you get some complementarity constraints which say that either lambda is 0 or I'm in collision. And you can write that down as an integer constraint, and everything I just said is still true. Everything still lives on a polytope. It's piecewise polynomial. The only thing is it's not continuous anymore. You can have discrete jumps in your solution. Okay, so why is this problem not solved? Why is that not everything I possibly need? If I could solve this explicit MPC, then I've got a controller that I can pre-compute. I could execute online on the robot, and I'm done. The problem is that the number of polytopes is doubly exponential. right? So, and that's where the picture comes in if we want to wake up the laptop real quick. Okay, thanks. All right, so this is the kind of polytopes that come in. Well, those are some trajectories, okay? This is just for a double integrator, x double dot equals u, okay, with input saturations. As you increase the number of times, the number of polytopes you have to think about grows doubly exponentially. So that's no good. So that's why we need approximate versions of it, okay? So the question is, well, first observation is we can take your plans and magically make them better by exploiting the KKT conditions and finding out the solution over a region instead of a point. Cool, we should leverage that. But then can we do something that makes this sort of solves almost this over the space enough that I can execute on the robot without the need to sort of solve it to optimality? I feel like that's an extremely geometric combinatoric problem you guys should be good at. And the fact is, right, if I were to write down the grasping problem in this framework, it's going to tell me I have 10 million integer variables, deciding by enumerating every possible point on my finger that I can possibly be touching the marker with, and it's going to explode into this huge thing. But my grasping policy just shouldn't be that hard, right? I mean, I shouldn't have to enumerate 10 million contact sequences in order to just figure out a controller that goes like this and grasps stably and has a stable dynamics, not just quasi-statics, but dynamics. So I think low degree approximations of that problem should be extremely viable for the real world. And we can sample from the optimal solution whenever you want. You just have to solve an MIQP. That's slow, but you can ask for the optimal solution at any point. And we know geometrically, locally what it looks like. So just finish that story for me, and we've got something, right? My robots will stop falling down. Yeah? Any ideas or any questions or anything like that? Yes?
It sounds like you're kind of framing it like an optimal control problem, but what you're describing, I'm wondering maybe there's kind of the more robust, like what you're looking for is the most robust stabilization instead of, I don't know, an optimal controller.
So I don't give a hoot about being optimal. I just want to not fall down. I think robustness is more important than optimization. You can put robustness into the MPC type frameworks and turn a lot of the same cranks. I completely agree. And optimality for me is just a way to make the problem precise, to specify the outcome of my algorithm. But I don't think being optimal is required. Being feasible would be good, and that does impose some constraints on my approximation. But I agree with you. Optimality is not necessarily required. Yes?
So I'm wondering here how much you have to solve this problem online and how much you can pre-compute, because if you've just got 2 feet and you can kind of parameterize your space pretty well, couldn't you just run this on a cluster for a year and get all those millions of polytopes?
Yes. I mean, so the motivation for the explicit MPC community getting as far as they did, and there's actually, I should say there's a great paper you can look up if you want to see this open problem by Alessio and Bimparada in 2009. You'll find it easily with that. Right, so the motivation was twofold. One is, can you just pre-compute so that the runtime is faster, like the lookup time is fast. The other reason to do this is if you have the explicit solution solved, you can do verification and other things, right? You can guarantee what this, as opposed to relying on a numerical algorithm. But despite computers being faster and everything like this, that doubly exponential thing still gets you so far, and people haven't done them for big systems. For instance, industry has embraced MPC. You haven't, and there is an explicit MPC toolbox in MATLAB. You can ask people for the solution, but that's not being used to the same amount. And I'd like to think computation will come in and save the day. I think data structures are going to make that. I mean, even the lookup could get expensive. I think data structures are going to have to come in and help. So I don't know, what the next few years will bring on that, but I agree.
Yeah. So similarly, how much? I guess is. Oh, okay. There we go. So how much are you able to or willing to use some sort of learning from initial states and trying to just approximate the function?
I love it. I think you could, for instance, another solution would be to make MIQP fast enough online that you could solve. If I could just even learn the active set, right? If say when I'm here, here's a reasonable active set to try, and then do sort of warm starting on the fly. These are all good problems, good possible solutions to this problem.
And
All I want is to be able to get the answer from a mixed integer MPC formulation fast enough to execute.
Go look at transactions on robotics right now. So a paper of mine just came out on this.
Okay, cool.
So I have also a question right here. Yeah. So if you actually change this formulation a little bit and you just make it a general optimization problem where or a trajectory optimization problem where your dynamics is not continuous, would that not be exactly the same problem? Because if you take John Kenny's simulator that he showed, this impulse-based thing or so, as your dynamics, and then just have some cost, and then see what happens if with a general optimizer that can handle non-differentiable dynamics, then you should be able to solve your problem as well, no?
Okay, so bunch of ways to answer that in different steps. Okay, so first of all, the results I'm saying about the explicitness having this form depend on it being convex and linear and everything. So you change this to f of x, and I have much less to say. The community has much less. There's much less to be said. I wrote down the discrete time version of this, which would be like the time-stepping solution to the differential equation, to avoid the impulse dynamics that John talked about, which I think the work with Mertig is fantastic and good. It complicates the analysis. You can do the continuous time version of this too. It's just that your forces have to have delta functions in them, and so you have to think about that complexity. Taking a fixed time step and doing time averaged forces resolves that. And it's been good enough for LCP simulation, so maybe it's good enough for this sort of control also. Yeah?
Yeah, but you care more about the analysis of your solution than...
I just want the robot to stop falling down, man.
So but you think the robot will stop falling down if you can analyze what comes out of the optimizer instead of just having a solution?
I think the robot will stop falling down if I can. I think I like nonlinear dynamics a lot. I want the efficiency to come out of a swing leg dynamics. I want all these things, but I actually think that the nonlinear dynamics are not the essential part. I think the essential part for just local stabilization is this combinatorial structure. I'd like to know that if I push it this way, I can take a step to recover. Right? That's what I'd like to come out. I'd like a feedback controller that just sort of is smart enough to go like this by a design that is as robust as LQR for a quadrotor. And this is one way to get that if we can solve this efficiently.
So let me just jump in really quick on this. So first, I think this is a fantastic problem. First and foremost, I share your sentiment on not wanting robots to fall. I wonder a couple of things, though. I wonder first if our control implementation paradigm should inform this discussion, right? So if you want to make a robot stand and you use torque control and you put in the reaction forces there, right? It's incredibly sensitive, right? You've seen it in simulation too if you're doing torque control. Well, if you put that in position mode, zero all the joints, you can shove it, it can rock a little bit, and you're just fine, right? So in some sense, I wonder whether the way in which we handle context at an embedded level, I'm not saying we should do everything in just straight position control, but I wonder if the way we implement things can inform this to some degree, at least in terms of robustness.
It won't take a step. Your position
No,
control
it will not. No. That's step two. So that's step two. Step two of the question or comment is so now what you're doing there is planning and control all in a single loop in some sense. That's what MPC is, right? You're looking forward in the future and you're developing a controller. So the question is, should we also be separating that out? So there's certain things that are more robust in an instantaneous way. For example, control Lyapunov functions, which you can get from LQR controllers, right? And then you could bring that with f of x longer term planning in terms of an optimization problem that now is not convex at all and is really hard to solve, but there's some computation tools. So I guess I'm asking is, I think this is a great problem, but another way to view it would be to separate out nonlinear dynamics, f of x for that, swing leg dynamics, and then understand how that generates a plan, and then understand how to implement that properly at the embedded level in a robust way in some sort of Lyapunov framework. So do you split the problem?
I completely agree, and that's actually why I'm saying local is okay, because what I think that's local to a fixed point is the easy case. but local around the trajectory is another simple case. If I can do the local stabilization, now with a time-varying matrix along a trajectory, then all this still holds. The thing that I want from this that we don't have yet in your world and my world is that if I end up on a slightly different contact mode than my plan was, I still know what to do.
Yeah.
That's what this would give me that we don't have yet.
No. Agreed. I mean, contacts are everything. Yeah.
Right?
Really hard.
You had a question, yeah?
Hey, boss. I think my understanding of the explicit MPC is like that you can sample in your initial state, and I think currently the optimization method is fast enough, so you can I'm not saying you can exactly search for your the configuration space. Probably you can sample a lot, and probably a lot, and then you kind of using some machine learning algorithm, you can give some intuition what's going on. And I think then you can form a feedback controller or a planning algorithm based on your the sampling and all the results you get from the optimization.
Let me try to say that back to you. Thank you. I think that's maybe not the way the traditional explicit MPC thinks about it, but if you're saying an approximation, and I agree that if the properties I said are true, which is that you can sample from the optimal policy at cost, you could generate a bunch of data and then fit that with a function approximator with machine learning. I think that could be a great approach to do it. I think, yeah, and I would love for that approach to be thoughtful enough to give asymptotic results on how close your approximation gets with the amount of program data, possibly clever sampling strategies which leverage the fact that we know where these polytope edges exist from that sample. Yes, please, this would be great. Feasibility has to work in there, so there's some constraints that have to be satisfied by my approximation, but love it. Can we do that? That would be awesome.
Okay, so let's move on to the next question. Let's first thank Russ for this very interesting problem.